Okay, so my name is Kunkun Tang. So I'm a very new user of Parsl, and I'm going to talk about uncertainty quantification with Parsl in composite material modeling. And this is a work realized in CSD, which is newly funded the P3 Center at NCSA, University of Illinois. So let me start with some of the CSD objectives. So one goal is to establish predictive confidence using UQ-based integration of multi-scale and multi-physics models and exploiting HPC to resolve scales. And on the other hand, to advance a physics-based prediction capability for novel carbon composites that will advance scramjet propulsion. So our initial studies focused on carbon fiber microstructure, which is a common key feature of high temperature composites. And Parsl will be used to manage workflow and provide provenance.
Great point.
This figure is this is Act 2 facility at the University of Illinois, and which will provide much of the data for prediction targets. On the right is the some of the preliminary simulation of supersonic combustion in this facility. So next, about uncertainties in this material modeling. So we of course have different candidate models for material microstructure and for material properties and for crack models. So for material microstructure, of course, we have different chemical composition. And on the other hand, about topology, for instance, in this figure is on the left is simple cylinders. In the middle is a sphere bed with different diameters. On the right is a foam fiber with the uniform void diameter. So about our workflow of codes, so we have been using, for instance, three codes here, so BUMA, GMesh, and WAP3D. And BUMA, which is a porous media microstructure analysis code developed in NASA, and it has been developed to compute effective material properties and perform material response simulations on microstructure of these porous media. And we have been using this to generate microstructures and surface mesh in STL format. And we then use GMesh to make a conversion from STL format to Nastran or Batran by creating a data mesh. And later then we use this tool, WAP3D, developed at the University of Illinois for finite element analysis. So in this talk, I will give a very simple example of PUMA generated microstructure and to do UQ with the computed effective thermal conductivity. And in backup slides, I give an example for GMesh plus WAP3D simulations. So here is an example of PUMA input and output. So input is very simple. A single CPP file contains all hard-coded parameters for now. So for instance, these domain size, fiber diameter, and fiber length, and orientation, porosity. And the output, for instance, is just a single STL surface mesh file. So here is an example of PUMA generated random fiber configuration. So on the right is the structure. On the left is the structure. On the right is a temperature profile when we impose a gradient in temperature in the x direction. And our quantum interest in this case is the thermal conductivity in 3 dimensions. And our goal is to know how microstructure properties and uncertainties affect our quantitative interest. So, so here I give a list of uncertain parameters. So for instance, for the material topology, we have the orientation parameters and fiber diameters, and the porosity is nominal value and uncertainty range. And about material properties, we do have fiber conductivity in both directions and air conductivity. So we have 11 parameters, and typically this requires hundreds to thousands of simulations. So next. So this starting point and workflow is very simple. It's just the two parts. It's the conductivity simulation plus UQ analysis. And I did a Jupyter notebook using Parsl for these problems. And I really like the fact that the Parsl it's very easy to use the bash decorator to call external application in Parsl. And here is the output of this Jupyter notebook simulation is the global sensitivities, which are used to rank parameter importances for this case. And three quantities of interest are shown, and for three of them, the porosity is determined to be the most important one. And yes, and these parameters sorted in descending order. So ultimately, our workflow will be much more complex than what I presented, before. So because we will have a couple of a wide range of codes for different lengths and time scales. So for instance, from nanoscale and to full scale, including supersonic combustion in the active facility, including wall material degradation. So I think the time probably is. So let me conclude with this final slides. So our plan is to use Parsl to manage complex workflow involving UQ-based integration of multi-scale and multi-physics models. The primary goal is on one hand to tackle coupled material modeling codes, and on the other hand is end-to-end UQ analysis. And some of the challenges we encountered is when I do some multi-cores performance studies, some issues have been observed in the coupling between Parsl and certain application codes, for instance, BUMA in this case. And so the thing is that it runs much slower, probably 20 times slower when we run in multi-cores. And that's it. And some special thanks to some of the wonderful people I work with listed here. Thank you.
Great. So we've got 2.5 minutes left for questions, if anyone has any.
I have a quick question, Ben. First of all, thank you so much. This was a really interesting talk. I really enjoyed it. At the beginning, you mentioned something about provenance. So I was wondering if you can just maybe elaborate a little bit on what your plans are as far as what kind of provenance requirements you have, or what kind of work you're going to do in that, as far as incorporating that into this project?
So my understanding is that because we will have in this slide we will have a lot of codes, and some code will at the beginning and some other code will come in the middle way, and the data data arranging and how this produced and data dependencies between these different parts components of our workflow will be very complex. That's why I mentioned this. But however, I'm a very new user in Parsl, so I do not know very much about that for now, but that's part of our plan.
Mm-hmm. Great, thank you.
Yeah, thank you.
Hey, Kunkun, just really quickly, just because we had the Dakota talk right before this, I can't remember, is Dakota one of the things that could be used for the UQ part of succeed?
Yeah, so I have been used the evaluation, I don't know, it's called tiling, right? I might remember in the past. And yeah, the thing is that it works very well for, for like thousands of simulations in one job submission. And however, it's and if I remember, I have to use relative nodes, and it typically use a uniform resource distribution across different simulations. And I Parsl, it's to me it sounds like a little easier to to manage these different resources for different simulations if I want to do them for different simulations. However, it's part of a challenge. Yes, I'm also thinking about combining these tools together.
Mm. And could you, as far as the shortening or the you're having some trouble with some applications running a lot slower, you said that was reported on the Parsl GitHub, or?
Well, actually, I contacted the people, so kind of tried, but it's so the thing is that for some for instance, for my sensitivity analysis code, it doesn't show this issue. It sounds like he's from Puma, and from Puma people, they say that they don't have issue because when they run different codes, the performance issue is observed anyway. So that's why I reported in GitLab in Puma community, Puma side.
Got it. Ben, we're gonna get in trouble with Ben, but I just want to encourage you to come to the Slack channel. Let's just make sure it doesn't get lost.
Sure, thanks. Yeah.
Yeah, come to the
Okay.
Slack channel and we'll talk about it. Make sure that we get it solved.